Kia ora koutou. This video is question 2E from this year's differentiation paper, and I'm going to do it, but I have some quite big reservations about it that I'm hoping didn't trip too many of you up in the exam, and I might as well talk about them at the start. I'm not the only maths teacher to have said this, and we haven't seen the assessment schedule from NCEA yet, so I'm hoping that you didn't get all confused by what I'm about to show you, but I'm going to show you anyway. So we've given a graph of a function, and this is the function here. So you can tell straight away we're going to be differentiating, probably using the quotient rule. K is a non-zero constant, and we're told that this graph has got a single turning point at Q. Now we know from, I guess even level 2, that a turning point is a point on the graph where the gradient changes, right? So this is a turning point here. If we've got a cubic, we've got a turning point here, and we've got a turning point here. A point of inflection is not a turning point, right? And what we end up finding in this question is a point of inflection and not a turning point. So I think there was a little problem with the question. But unless you did a graph on your graphics calculator to check and then freaked out, or you checked using the second derivative, then maybe in the exam you just would have done it, got to the end and thought, hey, that must be my turning point. But it's not exactly satisfactory. Anyway, I'm going to get into it now and just approach it how I hope you would have approached it on the day. Okay, so if we want to find a turning point, what we're going to do is differentiate the function here, and we're going to set the derivative to 0. We're looking for where the gradient is equal to 0. And then we really should be checking to see if that gradient has changed. But as I said, if we do that, it's not going to work. So we're probably going to freak out. So I'm just going to leave that step out for now. And because we're told that it's got a single turning point, what we're looking for is a situation where we have one solution to that gradient function equaling 0. And that's our strategy for solving the problem. So let's start off with my function. I've got y equals x e to the 3x over 2x plus k. Remember that k is a constant. So off we go with our quotient rule. dy by dx gives me this. I get 2x plus k squared. We'll plonk that up the top. 2x plus k times the derivative of x e to the 3x. Now using the product rule, that's going to give me e to the 3x plus 3x e to the 3x, right? The 3 and the e to the 3x are coming from differentiating that. And now I have to subtract the derivative of this. So I get 2 times my numerator. Now I've done that reasonably quickly because I figure at this stage of the year, you've probably done loads of quotient rule practice. If you're watching this at the very start of the year, you'll need to go quite slowly through this example. Now I'm going to clean that all up. I'm going to leave that 2x plus k squared sitting there in the denominator. So I'm not going to simplify this bit here with this bit here, because I know where I'm heading here is that I'm going to want the numerator to equal 0, right? Because we're trying to get dy by dx to equal 0. So we can take out a common factor, which is e to the 3x, and then I'm going to get times 2x plus k times 1 plus 3x, take away 2x, right? Now I could have done that step more slowly. If you need help with that, just leave me a comment and I'll put something into the notes. And then what we want to say here is that this has to equal 0 for a stationary point. So let's have a look at what we've got. Well, we can do a bit more expanding. We've got e to the 3x, and then we've got 2x plus k plus 6x squared plus 3kx. That's just expanding all of this. Take away 2x, and we'll leave the denominator as it is. We get that equals 0. Now I'm going to clean up the numerator. We've got 2x take away 2x, so we've got a little quadratic here, 6x squared plus 3kx plus k. I've lost something. What have I lost? feel like I've lost, oh yeah, no, that's right. Okay, cool. So we know that e to the 3x and 2x plus k squared must be greater than 0. So all we have to do here is to solve 6x squared plus 3kx plus k equals 0. So we're solving that, and for one solution, well, there's two ways to go here. We can either just get on with it and solve for x having one solution. We can do that either with completing the square or quadratic formula, or we can work with the discriminant and go from there. Because I know that I'm going to end up needing the x coordinate, I decided that I would do completing the square on this. So I'm dividing everything through by 6. I get x squared plus k on 2x plus k on 6 equals 0. Completing the square here gives me x plus 1/4 k. Take away k squared on 16 plus k on 6 equals 0. Now I think most of you watching, if you are kind of working at solid excellence level or scholarship level, you should be that confident with completing the square. If you're a bit wobbly on completing the square, then it's totally fine to do this with the quadratic formula. You're going to end up getting the same thing. And I know lots of you that I teach prefer that anyway. So here we go. We've got x plus k on 4 squared is equal to k squared on 16, take away k on 6. Getting a common denominator here gives me, what am I doing here? 3k squared minus 8k on 48. So the solution for x will be x equals negative k on 4 plus or minus the square root of this thing here. And if we're going to get one solution, then this bit's got to be 0. Okay? So we would have got to the same place using the discriminant. So one solution means that we must have 3k squared minus 8k equals 0. So k into 3k minus 8 is equal to 0. That gives me two options for k. Either k is equal to 0 or 3k is equal to 8 and k is equal to 8/3. But if we work with this solution, we get trouble because that gives me, just going backwards to here, you can see that that will give me an x value of 0. So that gives us, hang on, x is equal to negative k on 4, and that would equal 0. Now we have a problem here because my function was this, going all the way back to the start. So if we've got both k and x equaling 0, we'd have a whole lot of stuff, but most importantly in the bottom we'd have 0 plus 0, so it's undefined. Right, so that means that this function doesn't work for k equals 0, so we're going to reject that. So k can't be 0, k must be 8 on 3. And when k is 8 on 3, x is equal to negative k on 4, which is equal to negative 1/4 times 8/3, which gives me negative, what do I get? Negative 2/3. And that was all we were asked for that question. Now, as I said, I haven't seen the schedule because it's too early. We just asked for the x coordinate of point Q. But we could pop in and get a y coordinate there. But more interestingly, if you go to GeoGebra or your graphing calculator and you graph that function, so the function that I'm graphing now is this, x e to the 3x over 2x plus k, and k was 8/3. Right, so I did this, and this is the graph that we get. And there's a problem, right, because we don't have a turning point. We have a point of inflection. And you can't get penalized for it, but the question doesn't really make sense because there is I couldn't find a value of k that gave me a single turning point, and I played around a little bit more in GeoGebra. So I'm going to switch over to show you that now. Hopefully this will work. I won't be able to write on the screen, but I'll be able to use a slider thing that I set up. Interestingly, if you look at the algebra in here, remember that we got x equals negative k on 4 plus or minus this. So we're going to get no turning points for values where that discriminant is negative. And if you think about where that is, that's going to be, this is an up the right way parabola. My critical values are k equals 0 and k equals 8/3. So for the values between here and here, we should be seeing no turning points. And for all the other values, we should be seeing 2. So let's see if this is going to work. Where's my GeoGebra gone? Hopefully, here we are. Okay, so I'm going to move the slider a little bit. Sorry that this is so clunky. There we go. So up here, you can see that as I change the slider, the graph changes. And that's an a of -2. So that's a place where I've got 2 roots. It's quite hard to see them without playing around, but they're on the screen now where it says extremum at points B and C. Now it's very, very hard to see because of the scale that B is a turning point, but it is. And as we play with the slider a wee bit more, we get some quite cool things happening. It's just that sometimes in the exam is not the place that you want cool things to be happening, as you know. So here we go. You can see some interesting stuff happening here. And if I put the slider into the range between 0 and 8/3, we get, I think that's where we're getting no turning points. Oh no, we are getting a turning point. Anyway, thanks for watching till the end of me playing with GeoGebra. Hope you didn't find that too frustrating. It'll be interesting to see what they say in the schedule about this question, or if they communicate with maths teachers about this, because I think a couple of people probably have asked NCEA about it. I'll do question, the one with the triangle, probably tomorrow if I haven't done it already, and that's a really nice question and much more straightforward with what we've got to do. Thanks for watching.